Hello, this is Mrs. Roberts, and this is my Algebra 2 class that I'm trying to flip. This is Chapter 11 on Statistics and Probability, and this is the second lesson in this chapter. It's on theoretical and experimental probability. Our objective is to simply calculate theoretical and experimental probabilities. Probably we need to know what those are. We have a couple of different vocabs today. 2 pages of vocab, so if you need to pause it while we're going through these, make sure you do that so that you can get all these down in your notes. I'll be checking for those of you that are watching this. So for the vocab from 11.2, probability is the measure of how likely an event is to occur. They are written as fractions or decimals from 0 to 1, or as percents from 0 to 100%. If it happens, it's 100% likely to occur, obviously, and if it doesn't happen, it is 0% likely to occur. An outcome is a possible result of a probability experiment or a situation. For example, rolling a 1 on a dice would be an outcome. It's a possible result that you can get when you roll a dice. Flipping a head would be an outcome. Sample space would be all of the possible outcomes. For example, on a dice, all of the possible outcomes are 1, 2, 3, 4, 5, and 6. If you're flipping a coin, the possible outcomes are heads or tails. So pause this if you need to. Make sure you get all those vocab words, and I believe we have a few more. We need to talk about theoretical versus experimental probability. Theoretical probability is the ratio of the number of favorable outcomes to the total number of outcomes. It's the probability that it should happen. Please make sure you put this in your notes along with this equation. That P of the event means the probability of the event. And again, it's the number of favorable outcomes divided by the number of total outcomes in the sample space. So for example, if we're rolling a dice and we want to know what is the possibility of rolling a 5, we have 1 chance of rolling a 5 out of 6 possible choices. So we have a 1 in 6 chance of rolling a 5. That's theoretically. It means what should happen, just like flipping a coin. You have a 1 in 2 chance of getting a heads, and you have a 1 in 2 chance of getting a tails. Experimental probability is when you actually conduct an experiment and you look at the probabilities for that particular experiment. It's the ratio of number of times an event actually occurred to the total number of trials. It's the probability that it did happen. Again, probability of the event is equal to the number of times the event occurs over the number of trials. So for example, if I roll a dice 10 times and 3 of those times I get a 5, then the experimental probability is 3 out of 10. We would expect it to happen 1 in 6 times, but it happened 3 out of 10. Same thing with flipping a coin. If I flip a coin 10 times and I get heads 8 out of 10 times, we would have expected it to happen 5 out of 10 times because that's the probability, theoretical probability, but the experimental probability is what actually happened in a particular situation when we actually do the event. We have one more vocab word. The complement of the event is the set of all outcomes not in an event. Probability of A, the complement of A, that's what this line over it means. Probability of the complement of A plus the probability of A is equal to 1. Or the probability of the complement of A is equal to 1 minus the probability of A. In my example of rolling a dice, if I'm looking for a 5, make sure I've got my pen here. Okay. All right. If I'm looking at the probability of rolling a dice, and I'm looking for a 5, then the probability of rolling a 5, we said, was a 1 in 6 chance. So what's the probability of not rolling a 5? Would be a prob of 1 minus 1/6, or 5/6. And that should make sense to us because if we don't roll a 5, then we've rolled a 1, 2, 3, 4, or 6, which is 5 out of 6 possible outcomes. All right. Below is the sample space for a pair of dice. If we roll 2 dice, these are all of the options that we could have for rolling 2 dice. Okay? What is the probability you roll a 5? So what we need to do is we need to look for any place where we could roll a 5. There's one where we roll a 5. There's one where the 5 is rolled. Here's where a 5 is rolled. Here's where a 5 is rolled. Here's where a 5 is rolled. Here a 5 is rolled. But also, all of these have where a 5 is rolled. So we can simply count those up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 possible roles that include a 5 of them. Then we say, well, how many total rows are there? Well, there's 6 rows and 6 columns. So there's a total of 36 possibilities. What's the probability that we roll a 5? We have an 11 in 36 chance. What is the probability that we roll a sum of a 4 or more? Should you try that one? Pause it when you're done. Pause it for you to work on it, excuse me. Pause it when you work on it. And see if you got the right answer. All right, let's try. All right, so what's the probability that we roll a 4 or a sum of a 4 or more? All right, that's not a sum of 4, that's not a sum of 4. All of these have a sum of 4 or more. All of these have a sum of 4 or more. All of those have a sum of 4 or more. All of those have a sum of 4 or more. So do those, and so do those. All right, so we really only have 3 that didn't, which means we have 33 out of 36 possible ways to roll a sum of 4 or more. What is the probability, though, that we roll 2 4s? Well, there's only one option here, so our probability that we roll 2 4s is a 1 in 36 probability. These are all theoretical. This means if we expect things to happen on a random, or as they should, we should have it, all things being equal, we have a 1 in 36 chance of this happening. All right, let's take a look at our next example. All right, the Show Me Cash game from the Missouri Lottery is a game where you pick 5 numbers from 1 to 39. What is the probability that you select all 5 numbers correctly to win the jackpot? All right, this takes us back to some of the other ones that we did yesterday with the fundamental counting theorem, or we could also look at it as a permutation. Make sure you pause it, or let's do this one together and then I'll have you pause one. What's the chance that you win? Well, there's only one winning ticket to have all 5, but we need to know what are the odds that we pick the correct one. We could look at this as 39 times 38 times 37 times 36 times 35. 1, 2, 3, 4, 5. There's my 5 numbers. That would be right here what's in the denominator. We can multiply that out. Or we can also think of that as choosing 5 numbers out of 39. It's a combination because the order does not matter. So we pick 5 out of the 39 numbers. Okay, I don't know what that is off the top of my head, so I'm going to use my calculator. I'm going to find my PBR button. I'm choosing from 39 things, so that's my N. I need to choose 5. I need a combination, so I need to go probability, choose that NCR button, and choose 5. And when I get it, I get 575,757. That is your chances of winning a lottery with 39 numbers where you have to pick one. Can you see who's got the advantage there to pick, choosing lottery? All right, we can also look at things geometrically speaking. It says if a point is inside this 12 by 9 rectangle, is picked at random, what is the probability it will be inside the shaded region? So in other words, inside this blue region. Well, the entire region is this 12 by 9 rectangle. So we're going to put in our bottom, in our denominator, our 12 times 9. 12 times 9 is 108, and it's meters squared. Now, notice that these are broken apart into 3, and there's a reason for that, okay? First of all, we only want this triangle piece, but we can't have this square piece. So we're going to take this triangle and we're going to take this square out of it. So we need to find the area of the triangle. 12 times 9 is the total area. We need to find the area of the triangle. It has a base of 9 and it has a height of 12. Remember, the area of a triangle is 1/2 base, which is 12, times 9, which is base is 9, 1/2 base times height. 1/2, 9 times 12. That's going to be 54. But we have to take out this square because it's not shaded. Well, it's a square. It's 3 meters long, so it's also 3 meters high, which means it has an area of 9 meters squared. 54 minus 9 is 45. Okay, so what is the probability? We have 45 out of 108. Now, we could simplify that. I believe that 3 will go into both of those. 3 goes into there 15 times. 3 goes into 108. Let's see, 36 times. And we'll actually simplify again because 3 will go into here 5 times. And 3 will go into here 12 times. So we have a 5 in 12 chance. We could work that out as a decimal if we wanted to. But that's the probability that if we randomly throw a dart or randomly pick a point at some point in that square, that we will hit someplace in that blue shaded region. All right, you try this one. If in the game of bag toss, players throw corn-filled bags at a hole in a wooden platform. If a bag that hits the platform can hit any location with equal likelihood, find the probability that the bag lands in the hole. Okay, so we're just talking about the top area. It's 6 inches in diameter for the hole. The entire length of this board is 4 feet, and the width is 2 feet. You try that probability, please. Okay, so let's think about that. Did you catch the trick here? This is in inches, and this is in feet. So you have to be careful there, don't you? You have to put them in the same. So if you did 4 times 2 for your area of your total, that would be 8 square feet. Otherwise, you'd have to put it into inches. 4 feet is 48 inches. 2 feet is 24 inches. And I would need to multiply that out to find that. If I take 48 times 24, I get 1,152 square feet. And looks like I forgot this up here. Excuse me, square inches. That label on the bottom one should be inches, not feet. Let's see if I can get my pen to come back. And change that from feet squared to square inches. All right. Now, the piece that it goes in here is just that little circle. So it has to hit that, which is, if we think of this in feet, remember the area of a circle is pi r squared. So pi times the radius. But if we're talking about in feet, the radius is 1/2 foot squared. So this would be 0.25 pi square feet over 8 square feet. That would be the probability that we land in the hole. If we think about it in inches, it's pi r squared, and our radius is 6 in terms of inches. So 36 pi inches squared. Either one of those is acceptable. Just make sure you're using your label and make sure that you did it correctly. Okay, those past examples have all been theoretical. It's what should happen. Now, we all know that things that should happen don't always happen in the way that they should, or things that we expect to happen don't always happen in the way that we should. If we flip a coin, we may not always get exactly 5 heads and 5 tails if we do it 10 times, or if we do it 20 times, we won't always get 10 heads and 10 tails. It happens slightly differently. That's what experimental probability is about. What you see before you is an example of experimental probability. we drew some hearts. We drew some cards out of a deck of cards. When we did that, we did it several times. Let's see if we can figure out how many times we did it. Looks like 20 plus 18 plus 17. Well, 18 and 17 is 35. 35 and 20 is 55. Looks like we did it a total of 70 times. So we drew the cards 70 times. When we did that, we get 20 and 18. No, excuse me, that should be 80 times. I cannot add correctly there. So let me erase that. All right. And let me grab my pen back. So it looks like we drew a card 80 different times. Now that might get a little old, but sometimes you can find a computer program that will do it for you, do a random generator. We drew 20 diamonds, 18 hearts, 17 spades, and 25 clubs, and we made a total of 80 draws. Okay. All right. So we want to know, what is the experimental probability that a card drawn from the deck will be a club? Well, how many clubs did we draw? 25 out of 80. So what's our probability? 25 out of 80. We can simplify that. 5 goes into both of those. 5/16, I believe. So that is the probability for this experiment that a card drawn was a club. It is not the theoretical probability. This is for this specific experiment only. Okay? What is the experimental probability that a card drawn from the deck will not, keyword there, be a heart? You try that one. Pause it while you're trying it. Come back to it. All right. So again, we know that there are 80 possible options, not a heart. 18 of those were hearts. So how many were not hearts? 80 minus 18, which would be 62. We have a 62 out of 80 chance, which if we simplify both of those, that would be a 31 in 40 chance that a card drawn from the deck was not a heart. Scroll up a little bit. What is the experimental probability that a card drawn from the deck will be red? Well, I kind of gave you a little hint here. Here's your red cards. Here are your black cards. Try this one. Pause it while you're trying it. Come back and check. All right. Again, total number of choices is 80, so that's always going to be in the denominator. Total always goes in the denominator. 20 and 18, we'll add those two things together. Gives me 38. So I have a 38 and 80 chance of getting a red when I did this experimentally. I can also divide those and simplify. That would be a 19 out of 40 chance. Now, that's pretty close to what our theoretical probability would be, because red is half of the deck. We would expect it to be a 20 out of 40. So that's pretty good. Doesn't always work out that way, but usually with the more trials you do, the more exact you get. All right, that's the end of today's lesson. For tomorrow, would you summarize what you've learned, think back over all these, and write at least one question you have about the lesson? I look forward to hearing what you thought about it tomorrow. Have a great day.